In today's episode, we have the team from Geometry Labs joining us to discuss what post-quantum cryptography in the future might look like, lattice cryptography, and research and development that they're working on for both the QRL and in the crypto and DeFi space. Let's dive in and learn a little bit in today's episode. Hey everyone, and welcome back to another episode of the Quantum Resistant Ledger channel, the place where you come for the crypto and stay for the quantum. We have an exciting episode today, and we are going to be covering lattice cryptography. We're going to be discussing R&D being done in the crypto and DeFi space. And with us today are the guys from Geometry Labs. And also with me for our show today is my co-host, Michael Strike, our Director of Outreach at the QRL. And we are also joined, as I said, Geometry Labs, by Mitchell Kravitz-Thayer, Brandon Goodell, and Adam Corbo. And myself and Michael, we're excited to have this conversation to absorb kind of a lot of stuff that you guys are working on. For those of you that are viewing this episode at home, not only is there going to be a bit of a real small learning curve, but we're just going to kind of be hearing on what you guys have been working on up to date, and then what's moving forward in the future. So where I'd like to kind of start out this conversation is, it's going to be a two-parter, is can you tell the audience briefly what Geometry Labs is first off, and then give us a little bit of backstory on how you came to learn about the QRL. I think this is a good starting point for the combo.
Yeah, so Geometry Labs is a decentralized finance and cryptography research and development lab. We're a team of engineers, scientists, mathematicians, developing the next generation of products and open source tools. We've got about a 10-person team. Fantastic team, has contributed to a very diverse set of open source ecosystems. Obviously QRL, ZCash, Polkadot, Monero, Icon, Balanced, Harmony, Nervos. We've got involvement in a lot of different projects. We have kind of three working groups. One of them is the cryptography working group focused on post-quantum crypto, which is Adam, Brandon, and myself. Then we have some DeFi products we're working on. And then we have a very large infrastructure wing that does DevOps, full stack development, lots of infrastructure, blockchain data handling, that kind of stuff. So we're really just excited to get involved in all the different ways you can kind of level up the space. And the way that we got into QRL actually started back in last May, 2020. We had been getting geared up to do some Monero research. I was chatting in a Reddit comment thread, and I had said oh, blah, 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 we need a quantum resistant ledger, but I had not heard of QRL. And someone was like, oh, did you mean QRL? And I was like, oh, what is that? And so I looked into it, got very excited. And Jack actually from QRL reached out to me one-on-one and was like, hey, would you be interested in getting involved, all of this? And absolutely, of course. So, hopped on a phone call, chatted with the foundation, learned about, highest priority research needs, and got digging. And so now we've been working with QRL for, I don't know, about 8 months, and have been really enjoying it. Very truly exciting research.
Thanks for kind of giving the backstory on that. And I think a starting question that would be nice to kind of lead into some more of the meat and potatoes of what we're going to be discussing is, can you give a general kind of framework, or at least lead us in this direction of what's the difference, whether I'm someone that's a bit newer to the crypto space or if someone that's been around the block for a while, what's the difference between standard cryptography, that Bitcoin uses, that the majority of cryptocurrency is using, versus the stuff that you guys are working on at Geometry Labs? Because a lot of our viewers watching are, to some extent, some are probably quite familiar with private and public key pairings, factorization with prime numbers, just different extents. But I'd like to kind of show where it differentiates, and then kind of, get them excited about where things are headed for post-quantum cryptography.
Sure, I'll take this one because this is what I've been focusing on. So Bitcoin uses elliptic curve signatures and SHA-256 hashes in order to construct the protocol, among a variety of other tools, right? But those are the two big cryptographic pieces to the puzzle: is a cryptographic hash function, SHA-256, and elliptic curve digital signature algorithms using, I believe, SecP256K1. which is a particular elliptic curve. It's like a species name, a SecP256K1. The problem is that elliptic curve cryptography is vulnerable to quantum computers, as hopefully most of the listeners to this or most of the viewers will know. So for example, if I have a Bitcoin key, and a really powerful quantum computer, and I have the Bitcoin public key, I can go backwards and try to find the private key, which basically makes the entire thing useless. And so quantum computers aren't really commercially viable for those purposes yet. So Bitcoin is still secure. And the parts of the Bitcoin protocol that are based on SHA-256 hashes are also thought to be secure against quantum attackers. But to have a system that has like this vulnerability to it, that has this like event horizon coming up in the future that is like some unspecified number of months or years away, where everything is just going to kind of fall apart. It's just like having all of Amazon using RSA keys. It's just sort of like a nightmare waiting to happen. And if you want to transition over to a post-quantum system, it's going to take a long time. So you can't start after the quantum computers have arrived. So Bitcoin has these problems, and so does Monero, for the record, except for different hash functions. And a variety, I think the vast majority of crypto coins have these problems. So the idea behind post-quantum cryptography is to base your cryptography on a problem that is just fundamentally hard to solve. That there's no known algorithm, and that like if you were able to come up with an algorithm, then you might be able to reduce your algorithm to solve a famously hard problem that would like cause the whole hierarchy of what we think is hard to collapse, right? So it's like, if you can break this, then good for you. You just won the Nobel Prize because you just caused the biggest house of cards in mathematical history to come falling down, right? In particular, we've been focusing on lattice cryptography, because lattice cryptography, okay, personally, it's because I have a soft spot in my heart. But the thing is, QRL is based on the extended Merkle signature scheme. So it's hash based, and it's one-time signatures, but these signatures have a hard time aggregating together, and they're big, and the keys are big, and they're bulky, and they're long. They take a long time to verify. But with lattice cryptography, just like with bilinear pairings in the elliptic curve world, you have all of these tool sets available for things like aggregating signatures, so you can make things more efficient. And so instead of having one-time signatures in like a hash-based setting, you could have one-time signatures in a lattice-based setting. Everything collapses down to like one signature, like Mimblewimble, right? It's basically make a post-quantum version of Mimblewimble if you were able to like design a protocol around it like that. So in a certain sense, the main difference between classical cryptography and post-quantum cryptography is that we know that quantum computers can break classical problems, certain classical problems, and it'd be better to base our post-quantum stuff on something that can't be broken, or at least we think if it was broken, it would be a really, really big deal. And in the meantime, we want to use some sort of like setting that is so flexible that you can build a nice protocol around it using things like Mimblewimble style aggregation, so that signatures collapse down into a single signature, even across multiple blocks, right? So I hope that answers the broad overview question of the difference between pre-quantum and post-quantum cryptocurrency tech.
Yeah, thanks, Brandon, for covering that. And where I kind of want to move into that of what you're talking with lattice-based cryptography. Michael, do you want to dive into asking him a couple of the questions that we had regarding how this would integrate into QRL's ecosystem? You want to go into that, and then I feel like this would lead us nicely into that in proof of stake, consensus, and maybe we'll talk about atomic swaps a little bit.
Yeah, absolutely. Can you hear me?
Yep.
Yeah. Okay. One thing I think is of particular interest, not just to myself, but likely to other people in the community and other people are watching this video, would be how the addressing scheme and how that functions differently in a lattice-based, in a lattice-based framework. So let's talk about, if I may phrase the question this way, let's talk about Bitcoin for a moment. Bitcoin, essentially, you start off with a 256-bit random number. How you get that number is dependent on the wallet, or whether or not you're pulling temperature variations out of the atmosphere, or you're just typing in or moving your mouse around. It's 256 bits of randomness or pseudo randomness at the worst. Those 256 bits are your private key, of which then you apply something called elliptical curve multiplication to, which Brandon alluded to, and then which is considered to be a classical one-way function, a very hard problem to solve, which Brandon also said. And then after you take those 256 random bits, you apply elliptical curve multiplication, you end up at your public address. Now, there's the public addresses. In the early days of Bitcoin, you could actually and you still can send directly to the public address. It's called pay to public key. Another thing what Brandon was alluding to was the integration of SHA-256. Now this transaction can be run through a hash function after the public key, and then you arrive at what's called the Bitcoin address. So to summarize, from private key to elliptical curve multiplication to public key, and then to SHA-256, and then to Bitcoin address, which essentially with most modern wallets is what gets written to the chain. However, obviously, if you've seen these other videos, we know that there's this threat that in order to sign a transaction with the node, you have to present your public key as proof of ownership of that transaction, and while that transaction is essentially sitting in mempool, even if the transaction type is paid a public key hash, that SHA-256, who's to say you don't have a rogue node? It's hey, I'm not going to broadcast this transaction. I'm just going to send it to the quantum computer over here instead. So you're sitting over here waiting. This is a possible attack vector. While you're waiting for the transaction, it's actually being processed by quantum computers. So, Brandon, what I'd like to know is from that process that I described on how Bitcoin works, because that's what a lot of people understand. Where are the deltas as far as how lattice cryptography fits into that? Is that fair?
That's a great question. So just like as you described, the secret keys are 200 or however many bit strings, right? So that number 256 for Bitcoin comes from the security parameter that was used to instantiate the scheme. And the goal is, if it's a 256-bit secret key, then that means that you have 256 bits of security in your public keys, right? So in the lattice crypto scheme, we have a similar sort of thing. We have a short secret key that is only a few bits, and then you're going to have this public key that's going to be corresponding to that. And that public key is a lot larger in lattice-based cryptography. But what's interesting about this is that the lattice cryptography stuff is basically your high school linear algebra class on steroids, with a little bit of like geometry thrown in. It's like a weird blend of algebraic geometry and linear algebra and convex geometry, and it's really kind of cool. So here's the idea, is that a secret key is going, you know what? I have a whiteboard. This is great.
Whiteboard away.
Yeah. So if you remember like high school linear algebra, you might be presented with a matrix problem, AX equals B, right? Now, I'm going to put an underline under the things that we call vectors. I'm going to leave the matrices as capital letters, and we don't need to worry too much about notation past that. Physics classes put an arrow above the letter oftentimes, right? So it would look like this, but it doesn't really matter whichever one we stick with as long as we're consistent. So the idea is that in a high school linear algebra class, even high school, you can learn how to solve this problem using Gaussian elimination. If you're given A and B, you can solve for X by just doing like reduced row echelon form, right? It's like all of that basic high school linear algebra stuff, except you end up with an exact solution that doesn't have any constraints at all on the coefficients inside of this vector. So you might end up with a really, really long vector. And the lattice-based problems that we're working with forgets about the B entirely, and just tries to find something that solves AX equals 0. Except again, Gaussian elimination makes this easy. So what we have to do is we have to put a constraint on this vector x so that it can't get too long. If you visualize it as like a multi-dimensional vector from physics, right? We need it to be not too long, because I can solve this and get a vector of pretty much any length, right? But if I can solve this and guarantee that every entry is an element of the set -1, 0, and 1, that's magic. Like, especially if A is a big random matrix of integers. Imagine like a 10,000 by 10,000 matrix of integers, and I want to find AX equals 0, but I'm only allowed to have bits like -1, 0, and 1 in there. Excuse me, trits, I guess, right? That's a hard problem to solve, because even like the world's best computers right now would be chugging for years trying to solve this problem, right? In fact, the size of the matrix A ends up being the security parameter. So going back to the secret key, a secret key in the lattice-based scheme is this X, okay? Actually, it's not quite this X. It's a pair of X's, X1 and X2. And the public key of these guys is a random matrix multiplied by them. So I go from my secret key to my public key by multiplying. So instead of using elliptic curve repeated multiplication or exponentiation as in Bitcoin, all we do is matrix multiplication, which is really, really great. And I'll tell you why. Because all computer hardware is based on just basically doing matrix multiplication over and over and over again. So this process gets to be super, super, super efficient. Even if the ending keys, the public keys, are big, this whole process gets to be very, very efficient. So including verification of signatures and things like that. So in Bitcoin, you have this short string, which you interpret as an integer, and then you exponentiate the group base point to get your public key. In our world, we have this big public matrix, which is sort of like the base point, and this is my private key. And in order to solve for the public key, I just multiply those two guys. Now, as far as designing a protocol with specific like addresses that can be reused multiple times, that's a complicated question that is significantly more in depth than this. For example, in Bitcoin, we take the SHA-256 hash twice. We hash it twice from the original public key, if I recall correctly, right? And so the ways that you would end up using these things is like a more detailed question of how to construct wallets and transaction protocols. But this is the basic idea. The idea is that your secret key is a short vector. And by short, I mean all of the entries are like bounded. And your public key is the image of that when you just multiply it by a matrix.
So what does this do to the transaction sizes? Is this what actually gets written to the chain?
Right.
This is because what I'm hearing is this is a lot about efficiency, right?
Yes. So the idea here is that the only thing that really needs to be written to the chain for many, 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 many transactions in a row is just the one signature and all the keys. You're always going to have the keys on the blockchain, no matter what. If you want to spend, you need to have that key somewhere so that you can pull it and verify it, right? Every single node needs to be able to verify that the keys that were spent in the transaction were legitimate. So they need to know what those keys are, even light nodes. But there's no reason to have multiple signatures. So if you design a signature scheme that's based on linear algebra like this, then you can do basic sums and linear combinations of keys in order to compute a signature. And because it's linear algebra, you can have certain commutativity relations so that you can do it one way first and then do it another way and get to the same answer. And this allows you to verify the public key, verify the signatures. But so the short answer is that all the signatures can be added up and checked all at once for a lot, like for many, many, many keys in a row. All the keys have to be published to the blockchain, but only one signature needs to be published in order to describe all the transactions inside.
That actually leads me into my next question. So you're talking about signature aggregation, which is a function of Taproot, actually, that Bitcoin is going to be moving towards at the end of the year. For signature aggregation, once it's written to the chain, if I'm not mistaken, that will make all transactions, a single transaction or multiple transactions, all look the same. which could be interpreted as possibly a privacy feature. Is that would you agree with that assessment as far as not being able to tell what the constituent parts of that part of the chain? Yeah.
Sure. So just like how Mimblewimble has certain weak privacy claims about how if you're spending with it, then things aggregate down and you have some minimal masking of who spent what. Because you have to be, so first off, the scheme that we've been looking into is still a one-time signature scheme. And all those one-time keys are published to the blockchain. And you have to be able to link that one-time input key with the output key in order to make sure that the transactions balance. So there's quite limited privacy gained from aggregation, but there's a great deal of storage efficiency gain. I can aggregate signatures logarithmically. So the signatures that are aggregated take log n space instead of n times however many bits the signature requires, right? So it's not so much a privacy feature. However, in order to come up with like a key exchange mechanism that works for this so that I can swap with you in a sort of a Diffie-Hellman sort of style way so that you can get a one-time key that I don't know even though I'm sending to you, that ended up being a fun little experiment with key exchange mechanisms and stuff like that. And what ended up happening is we started basically using a Monero style stealth address approach, but not for any stealth reasons. It was just so that you can have one single wallet key that can generate multiple one-time keys without compromising its security. And so we're using that sort of feature from Monero. And as a consequence, all of these one-time verification keys are basically stealth addresses. So there is some stronger, but still weak privacy guarantees compared to something like Mimblewimble. It's kind of a soft gray area, and like the more you push at it, the more it's not really clear what sort of privacy gains you might get from mixing in small transactions. And in fact, this is a problem with Monero, but that's a whole different podcast.
So I have that sounds amazing. I have one or two other questions. Based on what you've said, as you know, the quantum resistant ledger is a stateful hash-based signature scheme. The states need to be kept. It needs to be stateful and immutable in order so that keys do not get reused, because that would defeat the purpose of the quantum resistance. So as far as what is the equivalent of state-based or statefulness within this lattice-based framework? What does that look like?
Yeah, that's a great question. So the statefulness, technically these signatures are state-free. They're stateless. Which, by the way, traveling through airports with like books that are talking about stateless combustible hash functions, not a fun time. No, so these are like stateless signatures, and there's ways to. So normally a signature scheme, let's say a k-times signature scheme, would work like this: you generate k keys, and then you keep a track of which signatures you've signed with those keys, and then you have to remember to not use those keys a second time. Right? Because if you do, then you've given away your private keys on accident, and anybody can manufacture any of these signatures as many times as they like, right? So that's why we say that like a one-time signature scheme, don't publish more than one signature, period. So,
which if I may add, QRL, just so our audience knows, the blockchain automatically rejects signatures that have already been used for that reason. So that is part of our current production network. Please continue.
Yeah, I don't mean to like cause anybody to immediately like panic and then go sell their stuff. This is just
for clarification.
Yeah, oftentimes I speak in some generalities about cryptographic design, specifically because I want to mention where the pitfalls are and the pain points are, right? And so one of those pain points is giving away your signature too many times, right? But as Michael just explained, QRL prevents that. So. But my point is that, so for a k-times signature scheme that's stateful, you need to remember which signatures you've signed with which keys so that you don't reuse them. In this scheme, we can extend it to a k-times signature scheme if we like, without state. You just need to remember which keys you've used. You don't need to remember which messages you've signed, just as long as you don't reuse those keys, right? And so it sort of reduces the state requirements, which is great for local storage capacity on chain, right? Because if you don't need every node storing huge quantities of state, then you don't need to worry about it. But again, just like in QRL, you're still going to need to protect against people publishing a signature for a second time. The thing is, from what I've looked at, is that, oh man, this gets into some technical details that I don't want to go into any further.
We can save that for a second episode.
Exactly. So, yep.
Yeah, we can definitely hit this in the second episode.
I've got one other question then. Can you talk about the progress that's been made for proof of stake consensus? What type of proof of stake? You mentioned Polkadot. I'm actually a big fan of Polkadot myself. They use nominated proof of stake. What's being put together? What does that look like for the quantum resistant ledger?
Well, actually, we're discussing that right now. But one thing that's really nice about aggregate signatures, if they're done correctly, is they're not necessarily one way and they're not necessarily random, but they're unpredictable. Because if a single honest person produces a single honest signature that then gets aggregated with a bunch of dishonest signatures, that one honest person has polluted all of the aggregation method of all of the malicious people with their honest input. And then those malicious people have a very difficult time guessing what the aggregate signature is going to end up being. So if you want to have something that's not necessarily a random beacon, but an unpredictable beacon, you can just use these aggregate signatures as they appear in blocks, right? You have one aggregate signature per block and you maybe hash the last 5 or 6 of them together. And since they're all aggregate, if there was even one honest spender among all of them, they won't be able to predict the output. And then you can use that information to generate your next set of stakers, because nobody was able to bias the input in a way that they could predict to game the system, right? So now, but this is all very dependent on a specific signature scheme that you use and so on and so forth. But it's possible that as far as stake validator election systems go, aggregate signatures give that for free, which would be fantastic. But I'm still working on certain analyses related to that. So that's also another animal. But as far as the details of an actual stake protocol, maybe I should hand this off to Mitchell, but because we were just about to talk about this earlier today or yesterday, and we ended up not connecting.
Thanks for covering that. Instead of going in, I wanted to ask maybe a question or two about atomic swaps and how they'd be used with QRL, but I think we'll probably cover that in a part 2 video. What I want to do for the last question or two as we kind of wind down this specific episode is for those people viewing at home to kind of get a general sense on what the relationship is between Geometry Labs and QRL and the progress being made moving forward. Maybe this one's for Mitchell, but what does the QRL and Geometry Labs engagement look like as we move forward here, just to give people viewing this a little bit of a sense, and then we can cover it a little bit more as we move into part 2.
Yeah, so from a practical perspective, we're basically structured like an embedded research team with a specialization on these particular aspects. So like 3 of us are working on all these various different lattice cryptography mechanisms that QRL can implement. We have biweekly technical meetings with Peter and engineers. Generally, our focus out of engagements like this is we produce both a theoretical paper explaining what we built and how we built it, or how we secured it, parameter proofs, all of that. And then we also produce like small toy prototypes, right? So that people can actually play with it for themselves and see how the signatures are generated, verified, all of that. So this is like, an experimental prototype, but we'll make it publicly available. And we're actually going to do kind of a staged series of bounties where the first approach is we want to put out a bounty on the math and the theory. Obviously, we believe it to be secure, but the more eyes on it, the better, right? So that would be like the first stage is applied to the research in general. Potentially also a bounty on optimization. We're mathematicians and researchers. There's certain portions where I suspect like a low-level engineer could potentially get in and refactor a function to be way faster or something like that. So optimization bounties are also possible. And then I think there will be some kind of internal time where QRL engineers are working on examining and refactoring the code and all of that. And so once they start to move it towards production code, then we could do like implementation bounties. But that's kind of looking ahead a little bit.
That answers it pretty good. I appreciate you covering that, Mitchell. As a last question before we kind of wrap this up, is there anything else that's being worked on in the background that you're able to share that might be exciting for those viewing to maybe hear about? I know, as Brandon alluded to, obviously we could probably go technical really deep down a rabbit hole in itself, but is there anything on the surface level that that you guys could share from Geometry Labs side that could get people excited at home as far as maybe what is to come?
Yeah, Adam, do you want to talk about what you've been working on?
Yeah, so I mean, I've also been working on the lattice-based cryptography and such, but another project that we've been kind of working on, debating and looking through is, so there's the Enclave software, which is basically like a vault on the Ethereum network for storing keys and, Ethereum and stuff. And it's based on, hash-based cryptography currently in its current iteration, and that it allows you to securely store Ethereum, and it's secure against quantum computers, so it's very future-proof. And so what we've been considering is basically doing kind of the same thing and presenting it to QRL to be used in a similar way, except it uses lattice-based cryptography protocols that we've been researching for this project, and it's it's very it's way more efficient than hash-based, clearly in a lot of different ways. And it allows for, do basically the same functionality. There, you can add a lot more functionality with lattice-based stuff. It's very modular. It's something I really like about lattice-based cryptography. Also, multivariate too has something people haven't. And elliptic curve isogeny stuff, which is different from current elliptic curve stuff. But anyway, so we're working on basically possibly switching it over to lattice and coding in Solidity or I forgot the other language, but yeah, and that can potentially work as well. So that's another exciting thing to look forward to as well.
In addition to what Adam's been working on with Enclave stuff, we've been looking into the possibility of using adapter signatures in order to take these aggregate signatures and turn them into Lightning channel creators. So you can have a Lightning channel network on top of the quantum resistant ledger so that people don't have to settle onto chain until they have to. And that way it's like an expensive settlement base layer. And then most of the transactions happen in a Lightning style network. And then in addition to that, we're also looking into like making recommendations to QRL to use certain code-based methods of compressing blockchain data using secure fountain architectures so that even in the presence of malicious adversaries, even full nodes only need to store a fraction of the blockchain that they normally would, which is totally cool. But these are sort of like still in production in the closet. And so we're trying to prioritize right now because there's so much that can be done with lattice cryptography. It is extremely flexible. It's great. So
to your point, if when QRL ends up getting brought to scale and the state files start becoming larger and larger and larger, you're saying that the ledger and state files themselves could actually be decentralized as well, as long as you had met some sort of safety threshold as far as the number of nodes, something like that.
So basically so the idea of striping a blockchain was something that we discussed in Monero regularly of like, oh, what if a node's only store one out of every 8 blocks? But if you do that, then you need to like contact 8 times as many nodes in order to download the whole blockchain.
Like RAID 0.
Yeah. And so the question is, how do you do this in a way that doesn't require downloading enormous like contacting an enormous number of honest nodes and still be able to just have a small local copy of stuff, pull what you need occasionally from the network if you are filling in holes, and still be secure against like 1/3 dishonest or 50% dishonest. I believe 50% was the assumption in the original secure fountain architecture paper. And it's all coding theory. This is what blows my mind. We're talking about okay, we're getting into this. This chain of blocks has this hash header, which allows you to verify whether or not the stuff that you've gotten is like legitimate from your nodes. And so using that hash chain header and then just a basic coding theory like trick of XORing blocks in sets, you can end up building a peeling decoder so that you can pull blocks one at a time out of these like sections that have all just been XORed down into one animal.
It sounds like you're describing a torrent storm almost.
It's super cool. Secure fountain architectures are super cool. And honestly, and they're blockchain agnostic. So like pretty much every project could be doing this. Anyway, it's cool.
Yeah. Thanks for sharing that, Brandon. And as we close up this episode, as we mentioned earlier, we're going to do a part 2 build on this. We're also going to be doing a Reddit AMA where we go through, you can ask some more questions. We can dive into them further in the next episode. And along with, if you haven't already done so, subscribe to our YouTube show by hitting that bottom right button to make sure that you're up to date with the latest episodes. And as a last plug on today's episode, where can people, along with learning about what Geometry Labs is working on, where's a good spot for people to learn more about what Geometry Labs is doing? You guys have a handle, a medium, a post. What's kind of the starting point for those that are just maybe learning about what Geometry Labs is all about?
So we have a medium with a brief introductory article, and I think we'll be publishing more as it comes. We're actually, in the context of QRL, we have 2 articles that are coming out. They've actually been written, and it's just on my desk to read them. One of them is about the cryptography and kind of just like what exactly, how this lattice, signature scheme works, all of that. The other one that we'll be putting together, coordinating with Jack, is an article specifically about the implications for QRL and what we're building for QRL, what kind of things that will unlock, atomic swaps, those should be coming out soon, hopefully by time for the AMA. Also, for people that really want to get their hands on, we'll shortly be releasing the code base and extensive documentation. So in a couple weeks, anyone can just pip install the library and start playing with it themselves.
That sounds great. And guys, I appreciate your time, Adam, Brandon, Mitchell, and Michael, as always. And for those of you viewing this at home, make sure that you keep those digital assets secure. Thank you for keeping in a nice viewership with us today as we learn about Geometry Labs, lattice cryptography, and just all things post-quantum. And for you at home, have a great rest of the day, and we'll see you in the next episode. Thank you.
Thanks, everyone.